Ocean.
An ocean. The world ocean of classical antiquity, is a body of saline water that composes much of a planet's hydrosphere. On Earth, an ocean is one of the major conventional divisions of the world ocean, which occupies 2/3 of planet's surface. These are, in descending order by area, the Pacific, Atlantic, Indian, Southern, and Arctic Oceans. The word sea is often used interchangeably with ocean in American English but, strictly speaking, a sea is a body of saline water that land partly or fully encloses. Earth is the only planet that is known to have an ocean, or any large amounts of open liquid water. Saline water covers approximately 72% of the planet's surface, 3.6 x 108 km2, and is customarily divided into several principal oceans and smaller seas, with the ocean covering approximately 71% of the Earth's surface. The ocean contains 97% of the Earth's water, and oceanographers have stated that only 5% of the world ocean has been explored. The total volume is approximately 1.3 billion cubic kilometers, 310 million cubic mile, with an average depth of 3,682 meters, 12,080 feet. The ocean principally comprises Earth's hydrosphere and therefore is integral to all known life, forms part of the carbon cycle, and influences climate and weather patterns. It is the habitat of 230,000 known species, although much of the ocean's depths remain unexplored, and over 2 million marine species are estimated to exist. The origin of Earth's oceans remains unknown. Oceans are believed to have formed in the Hadean period and may have been the impetus for the emergence of life. Extraterrestrial oceans may be composed of water or other elements and compounds. The only confirmed large stable bodies of extraterrestrial surface liquids are the lakes of Titan, although there is evidence for the existence of oceans elsewhere in the Solar System. Early in their geologic histories, Mars and Venus are theorized to have had large water oceans. The Mars ocean hypothesis suggests that nearly a third of the surface of Mars was once covered by water, and a runaway greenhouse effect may have boiled away the global ocean of Venus. Compounds such as salts and ammonia dissolved in water lower its freezing point, so that water might exist in large quantities in extraterrestrial environments as brine or convecting ice. Unconfirmed oceans are speculated beneath the surface of many dwarf planets and natural satellites. Notably, the ocean of Europa is believed to have over twice the water volume of Earth. The Solar System's gas giant planets are also believed to possess liquid atmospheric layers of yet-to-be-confirmed compositions. Oceans may also exist on exoplanets and exomoons, including surface oceans of liquid water within a circumstellar habitable zone. Ocean planets are a hypothetical type of planet with a surface completely covered with liquid.
Earth's global ocean. Divisions.
Though generally described as several separate oceans, these waters comprise one global, interconnected body of salt water sometimes referred to as the world ocean or global ocean. This concept of a continuous body of water with relatively free interchange among its parts is of fundamental importance to oceanography. The major oceanic divisions are defined in part by the continents, various archipelagos, and other criteria. See the table below for more information. Note that the table is in descending order in terms of size. The Pacific and Atlantic may be further subdivided by the equator into northern and southern portions. A smaller region of the ocean can be called other names, such as sea, gulf, bay, and strait.
Physical properties.
The total mass of the hydrosphere is about 1,400,000 metric tons, 1.5 x 1018 short tons, or 1.4 x 1021 kg, which is about 0.023% of the Earth's total mass. Less than 3% is freshwater. The rest is saltwater, mostly in the ocean. The area of the world ocean is 361 million square kilometers, 139 million square miles, and its volume is approximately 1.3 billion cubic kilometers, 310 million cubic mile. This can be thought of as a cube of water with an edge length of 1,111 kilometers, 690 miles. Its average depth is 3,790 meters, 12,430 feet, and its maximum depth is 10,923 meters, 6.787 miles. Nearly half of the world's marine waters are over 3,000 meters, 9,800 feet, deep. The vast expanses of deep ocean, anything below 200 meters, 660 feet, cover about 66% of the Earth's surface. This does not include seas not connected to the world ocean, such as the Caspian Sea. The bluish color of water is a composite of several contributing agents. Prominent contributors include dissolved organic matter and chlorophyll. Sailors and other mariners have reported that the ocean often emits a visible glow, or luminescence, which extends for miles at night. In 2005, scientists announced that for the first time, they had obtained photographic evidence of this glow. It is most likely caused by bioluminescence.
Zones and depths.
Oceanographers divide the ocean into different zones by physical and biological conditions. The pelagic zone includes all open ocean and comprises further regions of depth and light abundance. The photic zone falls 200 meters below the oceanic surface and is where photosynthesis can occur and is, therefore, the most biodiverse. Plants require photosynthesis, deeper life relies on material sinking from above, sea marine snow, or another energy source. Hydrothermal vents are the primary source in what is known as the aphotic zone, depths exceeding 200 m. The pelagic part of the photic zone is known as the epipelagic. The pelagic part of the aphotic zone comprises regions that descend in vertical order according to temperature. The mesopelagic is the uppermost region. Its lowermost boundary is at a thermocline of 12 DEGC, 54 DEGF, which, in the tropics generally lies at 700 to 1,000 meters, 2,300 to 3,300 feet. Next is the bathypelagic line between 10 and 4 DEGC, 50 and 39 DEGF, typically between 700 to 1,000 meters, 2,300 to 3,300 feet, and 2,000 to 4,000 meters, 6,600 to 13,100 feet. Lying along the top of the abyssal plain is the ebischopelagic, whose lower boundary lies at about 6,000 meters, 20,000 feet. The last zone includes the deep oceanic trench, and is known as the hydropelagic. This lies between 6,000 to 11,000 meters, 20,000 to 36,000 feet, and is the deepest oceanic zone. The benthic zones are aphotic and correspond to the three deepest zones of the deep sea. The bathyal zone covers the continental slope down to about 4,000 meters, 13,000 feet. The abyssal zone covers the abyssal plains between 4,000 and 6,000 m. Lastly, the hadal zone corresponds to the hydropelagic zone, which is found in oceanic trenches. The pelagic zone comprises two subregions, the neritic zone and the oceanic zone. The neritic encompasses the water mass directly above the continental shelves, whereas the oceanic zone includes all the completely open water. Whereas the littoral zone covers the region between low and high tide and represents the transitional area between marine and terrestrial conditions. It is also known as the intertidal zone because it is the area where tide level affects the conditions of the region. The ocean can be divided into three density zones: the surface zone, the pycnocline, and the deep zone. The surface zone, also called the mixed layer, refers to the uppermost density zone of the ocean. Temperature and salinity are relatively constant with depth in this zone due to currents and wave action. The surface zone contains ocean water that is in contact with the atmosphere and within the photic zone. The surface zone has the ocean's least dense water and represents approximately 2% of the total volume of ocean water. The surface zone usually ranges between depths of 500 feet to 3,300 feet below ocean surface, but this can vary a great deal. In some cases, the surface zone can be entirely non-existent. The surface zone is typically thicker in the tropics than in regions of higher latitude. The transition to colder, denser water is more abrupt in the tropics than in regions of higher latitudes. The pycnocline refers to a zone wherein density substantially increases with depth due primarily to decreases in temperature. The pycnocline effectively separates the lower density surface zone above from the higher density deep zone below. The pycnocline represents approximately 18% of the total volume of ocean water. The deep zone refers to the lowermost density zone of the ocean. The deep zone usually begins at depths below 3,300 feet in mid-latitudes. The deep zone undergoes negligible changes in water density with depth. The deep zone represents approximately 80% of the total volume of ocean water. The deep zone contains relatively colder and stable water. If a zone undergoes dramatic changes in temperature with depth, it contains a thermocline. The tropical thermocline is typically deeper than the thermocline at higher latitudes. Polar waters, which receive relatively little solar energy, are not stratified by temperature and generally lack a thermocline since surface water at polar latitudes are nearly as cold as water at greater depths. Below the thermocline, water is very cold, ranging from -1 DEGC to 3 DEGC. Since this deep and cold layer contains the bulk of ocean water, the average temperature of the world ocean is 3.9 DEGC. If a zone undergoes dramatic changes in salinity with depth, it contains a halocline. If a zone undergoes a strong, vertical chemistry gradient with depth, it contains a chemocline. The halocline often coincides with the thermocline, and the combination produces a pronounced pycnocline.
Exploration.
Ocean travel by boat dates back to prehistoric times, but only in modern times has extensive underwater travel become possible. The deepest point in the ocean is the Mariana Trench, located in the Pacific Ocean near the northern Mariana Islands. Its maximum depth has been estimated to be 10,971 meters, 35,994 feet, plus or minus 11 meters. See the Mariana Trench article for discussion of the various estimates of the maximum depth. The British naval vessel, Challenger 2, surveyed the trench in 1951 and named the deepest part of the trench, the Challenger Deep. In 1960, the Trieste successfully reached the bottom of the trench, manned by a crew of 2 men. Much of the ocean bottom remains unexplored and unmapped. A global image of many underwater features larger than 10 kilometers, 6.2 miles, was created in 1995 based on gravitational distortions of the nearby sea surface.
Climate.
Ocean currents greatly affect the Earth's climate by transferring heat from the tropics to the polar regions. Transferring warm or cold air and precipitation to coastal regions, where winds may carry them inland. Surface heat and freshwater fluxes create global density gradients that drive the Merlin circulation, part of large-scale ocean circulation. It plays an important role in supplying heat to the polar regions, and thus in sea ice regulation. Changes in the Merlin circulation are thought to have significant impacts on the Earth's radiation budget. Insofar as the Merlin circulation governs the rate at which deep waters reach the surface, it may also significantly influence atmospheric carbon dioxide concentrations. For a discussion of the possibilities of changes to the Merlin circulation under global warming, see shutdown of Merlin circulation. It is often stated that the Merlin circulation is the primary reason that the climate of Western Europe is so temperate. An alternate hypothesis claims that this is largely incorrect, and that Europe is warm mostly because it lies downwind of an ocean basin, and because atmospheric waves bring warm air north from the subtropics. The Antarctic circumpolar current encircles that continent, influencing the area's climate and connecting currents in several oceans. One of the most dramatic forms of weather occurs over the oceans: tropical cyclones, also called typhoons, and hurricanes depending upon where the system forms.
Biology.
The ocean has a significant effect on the biosphere. Oceanic evaporation, as a phase of the water cycle, is the source of most rainfall, and ocean temperatures determine climate and wind patterns that affect life on land. Life within the ocean evolved 3 billion years prior to life on land. Both the depth and the distance from shore strongly influence the biodiversity of the plants and animals present in each region. Life forms native to the ocean include fish, predator, such as jellyfish, cnidaria, cetacea, such as whales, dolphins, and porpoises, cephalopods, such as octopus and squid, crustaceans, such as lobsters, clams, shrimp, and krill, marine worms, plankton, and echinoderms, such as brittle stars, starfish, sea cucumbers, and sand dollars. In addition, many land animals have adapted to living a major part of their life on the oceans. For instance, seabirds are birds that have adapted to a life mainly on the oceans. They feed on marine animals and spend most of their lifetime on water, many only going on land for breeding. Other birds that have adapted oceans as their living space are penguins, seagulls and pelicans. 7 species of turtles, the sea turtles, also spend most of their time in the oceans.
Mixing time.
Residence time equals the amount of the element in the ocean / the rate at which that element is added to, or removed from, the ocean. The mean oceanic mixing time, residence time, is thought to be approximately 1,600 years. If a given element in the ocean stays in the ocean, on average, longer than the oceanic mixing time, then that element is assumed to be homogeneously spread throughout the ocean. As a result, since the major salts have a residence time that is longer than 1,600 years, the ratio of major salts is thought to be unchanging across the ocean. This constant ratio is often referred to as Forchhammer's principle or the principle of constant proportions.
Salinity.
A zone of rapid salinity increase with depth is called a halocline. The temperature of maximum density of seawater decreases as its salt content increases. Freezing temperature of water decreases with salinity, and boiling temperature of water increases with salinity. Typical seawater freezes at around -1.9 degc at atmospheric pressure. If precipitation exceeds evaporation, as is the case in polar and temperate regions, salinity will be lower. If evaporation exceeds precipitation, as is the case in tropical regions, salinity will be higher. Thus, oceanic waters in polar regions have lower salinity content than oceanic waters in temperate and tropical regions. Salinity can be calculated using the chlorinity, which is a measure of the total mass of halogen ions, includes fluorine, chlorine, bromine, and iodine, in seawater. By international agreement, the following formula is used to determine salinity. Salinity, in %0, equals 1.80655 x chlorinity, in %0. The average chlorinity is about 19.2% 0, and, thus, the average salinity is around 34.7% 0.
Economic value.
The oceans are essential to transportation. This is because most of the world's goods move by ship between the world's seaports. Oceans are also the major supply source for the fishing industry. Some of the more major ones are shrimp, fish, crabs, and lobster.
Waves.
The motions which first present themselves to our notice are partial and alternate rising and falling of the surface is known as undulations or waves.
Extraterrestrial oceans.
While Earth is the only known planet with large stable bodies of liquid water on its surface and the only one in our solar system, other celestial bodies are believed to possess large oceans.
Planets.
The gas giants, Jupiter and Saturn, are thought to lack surfaces and instead have a stratum of liquid hydrogen, however their planetary geology is not well understood. The possibility of Uranus and Neptune possessing hot, highly compressed, supercritical water under their thick atmospheres has been hypothesized. While their composition is still not fully understood, a 2006 study by Torowich al. ruled out the possibility of such a water ocean existing on Neptune, though some studies have suggested that exotic oceans of liquid diamond are possible. The Mars ocean hypothesis suggests that nearly a third of the surface of Mars was once covered by water, though the water on Mars is no longer oceanic. The possibility continues to be studied along with reasons for their apparent disappearance. Astronomers believe that Venus had liquid water and perhaps oceans in its very early history. If they existed, all later vanished via resurfacing.
Natural satellites.
A global layer of liquid water thick enough to decouple the crust from the mantle is believed to be present on Titan, Europa and, with less certainty, Callisto, Ganymede and Triton. A magma ocean is thought to be present on Io. Geysers have been found on Saturn's moon Enceladus, possibly originating from about 10 kilometers, 6.2 miles, deep ocean beneath an ice shell. Other icy moons may also have internal oceans, or have once had internal oceans that have now frozen. Large bodies of liquid hydrocarbons are thought to be present on the surface of Titan, though they are not large enough to be described as oceans and are sometimes referred to as lakes or seas. The Cassini-Huygens space mission initially discovered only what appeared to be dry lake beds and empty river channels, suggesting that Titan had lost what surface liquids it might have had. Cassini's more recent flyby of Titan offers radar images that strongly suggest hydrocarbon lakes exist near the colder polar regions. Titan is thought to have a subterranean water ocean under the ice and hydrocarbon mix that forms its outer crust.
Dwarf planets and trans-Neptunian objects.
Ceres appears to be differentiated into a rocky core and icy mantle and may harbor a liquid water ocean under its surface. Not enough is known of the larger trans-Neptunian objects to determine whether they are differentiated bodies capable of possessing oceans, although models of radioactive decay suggest that Pluto, Eris, Skna, and Orcus have oceans beneath solid icy crusts at the core boundary approximately 100 to 180 kilometers thick.
Extrasolar.
Some planets and natural satellites beyond the Solar System are likely to possess oceans, including possible water ocean planets similar to Earth in the habitable zone or liquid water belt. The detection of oceans, even through the spectroscopy method, however, is likely to prove extremely difficult and inconclusive. Theoretical models have been used to predict with high probability that GJ1214b, detected by transit, is composed of exotic form of ice 7, making up 75% of its mass, making it an ocean planet. Other possible candidates are merely speculated based on their mass and position in the habitable zone include planet, though little is actually known of their composition. Some scientists speculate Kepler-22b may be an ocean-like planet. Models have been proposed for Gliese 581d that could include surface oceans. Gliese 436b is speculated to have an ocean of hot ice. Extrasolar moons orbiting planets, particularly gas giants within their parent star's habitable zone, may theoretically possess surface oceans. Terrestrial planets will acquire water during their accretion, some of which will be buried in the magma ocean, but most of it will go into a steam atmosphere, and when the atmosphere cools it will collapse onto the surface, forming an ocean. There will also be outgassing of water from the mantle as the magma solidifies. This will happen even for planets with a low percentage of their mass composed of water, so super-Earth exoplanets may be expected to commonly produce water oceans within tens to hundreds of millions of years of their last major accretionary impact.
Non-water surface liquids.
Oceans, seas, lakes, etc., can be composed of liquids other than water, for example the hydrocarbon lakes on Titan. The possibility of seas of nitrogen on Triton was also considered but ruled out. Underneath the thick atmospheres of Uranus and Neptune, it is expected that these planets are composed of oceans of hot high-density fluid mixtures of water, ammonia and other volatiles. The gaseous outer layers of Jupiter and Saturn transition smoothly into oceans of liquid hydrogen. There is evidence that the icy surfaces of the moons Ganymede, Callisto, Europa, Titan and Enceladus are shells floating on oceans of very dense liquid water or water ammonia. Earth is often called the ocean planet because it is 70% covered in water. The atmosphere of Venus is 96.5% carbon dioxide, and at the surface the pressure makes the CO2 a supercritical fluid. Extrasolar terrestrial planets that are extremely close to their parent star will be tidally locked, and so one half of the planet will be a magma ocean. It is also possible that terrestrial planets had magma oceans at some point during their formation as a result of giant impacts. Where there are suitable temperatures and pressures, volatile chemicals which might exist as liquids in abundant quantities on planets include ammonia, argon, carbon disulfide, ethane, hydrazine, hydrogen, hydrogen cyanide, hydrogen sulfide, methane, neon, nitrogen, nitric oxide, phosphine, silane, sulfuric acid, and water. Hot Neptunes close to their star could lose their atmospheres via hydrodynamic escape, leaving behind their cores with various liquids on the surface.